Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is just to give an example of how to mathematically describe motion in the plane. And what we're looking at here is this particle moving along this curve here. So this particle is moving in this direction in this example. The path is defined by the curve y equals ax squared, where a has a value of 0.25. It's just quicker and easier for me to write a throughout the equations, and I'll put that 0.25 in at the end. And what we're going to try to do is find the speed and acceleration at t equals 2 seconds given this information. Right, so again, the speed would be the magnitude of the velocity vector, and we're going to look for the actual acceleration vector, which would be magnitude and direction. Probably we'll just leave our answer in unit vector form. But once you have a vector in unit vector form, it's really easy to get them. You essentially have the magnitude and the direction. So I'm going to start this with drawing a position vector that describes the location of this particle. The position vector of this particle, right, at the instant shown looks like this. I'm going to go ahead and write out something to describe it. In Cartesian coordinates, that vector looks like xi plus yj, right, meaning that x being like this distance to the right, and then the I means to the right, and then this distance is y, and it's up, and hence the unit vector is given. So if I want to know something about the velocity or the speed of this particle, I can get that by differentiating this function. So the velocity is going to be x dot I. Now I'd like to point out that when you time differentiate this, x is definitely changing, so it has a time derivative. I in this example is not changing. I points to the right in this example. That's not going to change. So this thing's time derivative is 0. And I'd like to point out that's not always the case. There will be problems where later on in this course where this unit vector will be changing in direction. Next derivative, y definitely changing, so this is going to be y dot, but j not changing. Now, as I kind of look to the right, x dot, and when I meant look to the right, I meant over here, right? X dot is the rate at which x is changing. That's this value right here, just written in a different way. Velocity component x direction is 8 meters per second. So this is x dot. So this is a value that's given. Y dot we can calculate because we have this relationship between y and x. So I'm just going to do this off to the side. So y dot, looking right here, and time differentiating is going to give us 2ax times x dot. The x dot is coming into play because this is a time derivative, not a position derivative. If that were a dy dx, the answer would be just 2ax. However, x itself is time dependent, so by the chain rule of differentiation, this thing's derivative with respect to t would be 2ax x dot. And again, this term is coming from the chain rule of differentiating that function. Oops. And I believe these are all values that we have here. So I'm going to write this out. Our velocity is x dot I plus 2ax x dot j. And it looks to me like there's enough information to go ahead and calculate our velocity vector and our speed right now. I'm going to go ahead and put numbers into this. So our velocity is going to be, all right, x dot I is going to give us 8. And I'm going to put NCU for notes consistent units. That's 8 meter per second I plus 2ax x dot. That's going to be 2 times 0.25 times x, which is 8, times x dot, which is also 8. And again, the units are all consistent. When I write the units in on my computer, it ends up being pretty long. And since I'm kind of restricted in room, I'm just going to stick with my note consistent units. This will work out to meter per second. And that's going to give me a j. So our velocity vector is 8I plus, and if we work this product here, let's see, 64 or 128. That's a quarter of 128. 32. 32J. And these would be in units of meter per second. Now, to actually answer the question that I was looking for was the particle speed. So that would be the magnitude of the velocity vector. So the magnitude of v squared is going to equal 8 squared plus 32 squared. And I'm going to let one of my helpers here give me a value for that. .98. Let's just say approximately 33 meter per second. So there's how fast that particle is moving at that point. All right, next, let's start looking now for the acceleration vector. This stuff is not needed for that. So I'm going to go ahead and get rid of this because I need some room. I guess I don't need that either. All right, so to get our acceleration vector, we're just going to time differentiate our velocity vector. So that first term is going to give me an x double dot I. Now, x double dot gives the x component of the acceleration vector. And again, I is not changing in, well, it never changes in magnitude because it's a unit vector, but it's not changing in direction either, so it doesn't have a time derivative, or I should say its time derivative is 0. Now, when we differentiate this expression, keep in mind the a is just a number, a constant, so this is going to be 2a times, and what we need to differentiate is this line right here. And this needs to be product ruled, so the derivative of the first is x dot times the second. That's going to give me an x dot squared plus the derivative of the second. Now this is x dot already, so if we hit it with a time derivative, that's going to be x double dot, then times the first. And that's going to be in the j direction. All right, so now what we have is we have the acceleration vector. As I kind of look these over, x dot I believe we have. This I believe we have. What we're going to have to do is we're going to have to figure out x double dot. X double dot? Oh, yeah, that's right, looking here. Yeah, this is x double dot right here. Yep. I was just looking around for it going, wasn't that a known quantity? Yeah, right here. So acceleration x direction is x double dot, so our acceleration vector is going to be 4, and again, I'm going to use NCU for note consistent units. So 4I plus 2 times 0.25, I'll go ahead and just put numerical values in, times the quantity, let's see, x dot squared plus x double dot times x, and that's in the j direction. So it's going to be 4I plus, and I'm going to wait for one of my helpers here to give me a value for this, plus 48k. And again, this would be, oh, I'm sorry, 48j. Meter per second squared. Yeah, when these things get 3D, they get a lot more difficult, quite a bit longer. So I'm going to take a moment here and talk about these guys here. So if I were to draw that acceleration vector, and remember that when I drew this curve, I just sketched it by hand. It doesn't necessarily have the shape. But if this particle's speeding up, this would give us a component something like this. That's the tangential. And then the radius of curvature is over here somewhere, so there's a centripetal component, something like this. And then the net acceleration vector at the instant shown might point something like this. And that's what we've found right there. And again, if we wanted the magnitude of that acceleration vector, we would Pythagorean theorem this, square root of 4 squared plus 48 squared. So again, this is meant to be just a kind of a introductory example of how to mathematically describe motion, in a plane, specifically along some sort of defined curve. Have a great day.